Greetings of the day, my dear friends. As in previous lectures, we have studied the topics related to the applied mechanics, and in this lecture, we are going to study about the equilibrium. So, just start with the chapter equilibrium. So, as name suggests, the equilibrium, one can define the equilibrium which cannot be any system of forces which keeps the body at rest is said to be in equilibrium. Means when you are applying the different loads on a body, but even though if you are applying the n number of loads and body is being in rest and does not change its state of motion or its state, then that particular body is called as it's in a equilibrium. This can be defined as also when the condition of the body is unaffected, even though it is acted upon by number of forces, it is said to be an equilibrium. Means, as I told you, if you are applying a load on any body, obviously it is an example that if you are applying load on any of the body, then obviously, if, suppose I am applying load on this pen, then obviously this pen will start moving or it will start rotating. But when I'm applying a load on this pain and still this particular pain is not getting changed its state, then this particular body will be called as it is in equilibrium. So just have a look with the example of this seesaw. Here you can see that two different loads of A and B is applied, where you can just see that A is having so many of the mass and B will also having some another mass. Also, it is mentioned over here that the mass, or we can say that weight A is equal to weight B, and as weight A and B are saying, it is balanced one. It is balanced, right? You can see that nowhere this is upward and this is a downward. So this is balanced one, and the condition where your particular body is balanced, that will be called as a equilibrium. So this should be keep remember that this will be called as a equilibrium. Okay, so this was the definition. Now next, when we are going for the next calculation, we are supposed to calculate the resultant force. So because see, we have already seen in previous lectures that if we are having any of the force systems, suppose say a concurrent coplanar concurrent force system I am having, suppose say that it is F1 and F2. So for this F1 and F2, one particular force can be represented, which will be equals to R, that is resultant. So we can say that for representing the both force effect, we can just represent a single force, which will be called as a resultant. And that's why how to find out the formula for this R that we have seen over here. So resultant is equals to summation of fx square, because n number of forces will be acting upon the point. So you can just consider that, for example, if you are having 1, 2, 3, 4, likewise. So if you are having F1, F2, F3, and F4, likewise you will have n number of the forces. And in this case, what we have to do is that we have to just make a summation, just resolve these all the forces on the x direction or x axis, and again resolve all the forces on the y axis. Once you resolve all the forces on x axis and y axis, just make a summation. So resultant will be equals to R is equals to summation of fx square. Just add on all the x components loads, or the components of all the forces acting along the x direction, that we are going to take as a summation fx square, plus you have to take summation fy square. In this also keep remember that whichever force is going towards left side, that will be considered as minus, going towards downward, that will be again considered as minus, upward will be considered as positive and right side will be also considered as positive. So like this we have to take summation of fx square plus summation of fy square, and under root of these both summations will be called as resultant. Generally equilibrium is nothing but, just one second. Okay, so equilibrium means resultant force acting on the body is zero, because what we have seen that when you are having something like this and these forces, any of the forces f1 and f2, right? So if these two kind of the forces are acting and I am supposed to find out the effect of these forces, obviously if this by acting the f1 and f2, my body is being in equilibrium or it is being in rest condition, so resultant will be always what? Zero. The value of this particular formula will be equals to zero. That's why it is mentioned over here. The equilibrium means resultant force acting on the body is always being zero when your body is in equilibrium. And again, once if your body is in rest, the resultant is zero, then it's quite obvious that the summation fx is zero, and again summation fy will be zero. So whatever may be the forces that is acting over here, suppose see here, अगर मुझे एक एग्जांपल लेना है, यहाँ पर अगर फॉर एग्जांपल इस पॉइंट पे मेरा फोर्स अप्लाई कर रहा है, समझो 25 किलो न्यूटन का, अगर मुझे राइट हैंड साइड में 25 किलो न्यूटन अप्लाई हो रहा है, सो इट विल बी ऑब्वियस दैट इट विल बी move towards right hand side. So this body whatever may be present over here, that will moves by some displacement by applying 25 kilonewton on right hand side. If I am applying the same 25 kilonewton on left hand side on this direction, so this minus and this plus will create my summation fy is equal to 0, right? And then only my body will be in equilibrium, and that's why it is mentioned that when your body should be in equilibrium, the summation of fx should be equals to 0, and summation fy will also should be 0. Then according to the Barrington's theorem of moments, the position of the resultant can be found out. Okay, so what is Barrington's theorem that we have seen already? We can see in this particular content also. According to the Barrington's theorem of moments, the algebraic sum of the moments of all forces about any point is equal to the moment of the resultant force about the same point. As earlier in the previous chapter, we have seen that if we are taking the algebraic sum of the moments, so for example, okay, I will just make a point over here. Suppose if I wanted to find out the particular moment and this particular location, suppose this one, two, three forces are acting, for example, about this particular point A. So whatever may be the algebraic sum of the moment of these all the forces about point A due to force, that will be equals to always whatever resultant creating moment about this point A. So this is we have seen in previous lectures or the previous chapter also. According to the Barrington's theorem of moments, the algebraic sum of the moments of all forces about any point, whatever may be point you are considering, that will be equal to the moment of the resultant force about that same point. And that's why we can say that the summation of the moment, okay, we have seen that the algebraic moment, so the summation of moment, the moment can be calculated as the force resultant into distance x. But as we know that in equilibrium, the resultant is equals to what? It will be equals to 0. And that's why I have stated that as r is equal to 0, if I put this value into the r, obviously I will get what? The moment equals to 0. So in this case, when your body is in rest condition or in equilibrium, the moment will also be equals to 0. So this is very important thing. See, when we are saying that, obviously if my body is, suppose I am showing a body over here. Okay, suppose see here I am showing a body. It should not be moved. It should not be moved. It should not be rotated, right? Because it should be in steady condition, right? It should be in steady condition. So it should not be moved along x and y direction. It should not be rotated on any direction. So what the things we have come up along with this, that summation fx, summation fy should be equals to what? 0. And now we have got that summation of moment should also be equals to 0. So these three conditions that we are getting from the Waringer's theorem. So therefore analytical conditions of equilibrium for coplanar non-concurrent forces are, as I have told you over here right now, that the summation fx is 0, summation fy is 0, and moment is 0. So what are these summation fx, summation fy, and summation m? That is explained just below. If your summation fx, we are saying that it is summation fx. So the summation fx is nothing but algebraic sum of the components of all forces along x-axis, which should be equals to 0, as this fx is nothing but what? Algebraic sum of the components of all forces, right? And this summation algebraic sum should be what? It should be equals to 0. Then summation fy, obviously the algebraic sum of components of all forces along y-axis, which again should be equals to 0. And again, as we have seen earlier, that over here the summation of the moment, or rather we can say that algebraic sum of the moments of all forces about any point in their plane must be equals to 0. So what we have seen over here, that it should be summation fx is equal to 0, summation fy is equal to 0, and again moment will be equals to 0. So after this, whenever we are going for solving the problems, in that case, we have to prepare, or we have to draw a free body diagram. So what is a free body diagram? In statics, for considering the equilibrium of bodies under any force system, each body is separated from its surroundings. Such a body is known as free body. So just for an example, you can say that when we have a particular diagram, suppose I can say that I'm having a beam, some of the loading are acting over there, so that beam along with its cross section is not supposed to be shown on the analysis problem. So what I will do is that I will just take out the free body diagram. Just we can say, we can see in the another slide how the free body diagrams are created. Just look at over here, that if all active and reactive forces, just keep your attention over here. What are there? The active and reactive. What do you mean by active and reactive? Okay, over here it is mentioned, so we will just look over there. So all active and reactive forces acting on a free body are shown. The diagram is known as a free body diagram. Okay, so we are going to just see the free body diagrams just later on. So what are the active forces? The active forces means applied forces, the applied forces and weight of the body. Okay, whatever forces, external forces we are applying, and the weight of the body will be called as what? It will be called as active forces. You can say that this will be called as a live loads in design of RCC structures, and these all this will be called as active loads or live loads. Okay, whichever these active loads are there. So you should be remember that this active is nothing but live loads. And what are the reactive forces? The reactive forces means that the reactions offered by the floors, walls, strings, cables, hinged or roller supposed, etc. Wherever your body is raised, and due to the rest condition, whatever maybe the reactions are offered, that reactions will be called as reactive forces. This will be called as reactive forces. Okay. So like this, we are going to see the next content. We are going to see the free body diagrams of the some of the cases. So just consider an electric lamp which is connected by electric wire as shown in figure. A. It is separated from its surrounding as shown in figure B. And just see, we are having a particular free body diagram, or we are having a diagram of the lamp which is connected with the wire to a ceiling. We can say that this is the ceiling. So what particular thing was there, that we were having a lamp which is connected to the wire. So we can say that over here this particular force was applied on the bulb, or the weight was applied like this, and the reaction whichever may be provided, that was like this, and that's why it was in equilibrium. So you can just see that it is separated from its surrounding. In surrounding, what we have done, we have done, we have just removed all the surroundings from the body, and we have just mentioned the body in part B. Then in figure C, you can see that these are the active forces, right? W. And force is nothing but reactive forces. When you are applying the weight or whatever may be the load of that particular lamp is there, or the light is there, that is resisted by the T, and that's why the W is nothing but active forces. Okay, so this is a active force, and the T is nothing but what? It is reactive force, right? So like this we are having free body diagram. So after this we can solve the problem. Again, for some of the different condition, we have some different free body diagrams. Over here we can see that the free body diagram for a sphere resting on box. So you can see that here sphere is shown over here, and this is nothing but a box over here. If you see that this particular place, so over here the box is there. So what is happening over here, that this is nothing but a, again, active force. Over here it is active force. After that you can just see over here that it is rested over here, right? So it is touching, and obviously if it is touching, so somewhat reaction will be created over here, and another will be like this. So this will be a R2. So any one nomenclature which can be used, it is mentioned here as RA and RB. So you just see that likewise the free body diagram can be created. Okay. So next, free body diagram for a block resting on horizontal floor. Obviously if your body is rested like this on a floor, so self weight, that is active force, will be like this W, and reactive force will be like this R, right? So you can see that whatever created diagram is like this. Okay, so hope this theoretical content, whatever I have taught till now, that you have understood well. If you are having any of the doubt related to the content that is taught in theoretical part in this particular chapter, you can just put me a comment or can ask me directly. Thank you. Thank you very much.